Okay, hello everyone. Thank you so much for inviting me here. So let me introduce myself first. I am Wansop and working at the PSE team at the EF as a technical coordinator and also a researcher, uh, or I'm doing some eco dev work too. So today I just want to introduce about the how to use Schnorr signature, or actually maybe it can be replaced by some another signature scheme. But today what I want to share is about how to build the layer 2 sequencer for more application specific rollups. Yeah, let's start. Uh, I always say we have to commit optimistically and verify cryptographically. Um, many teams are already using this approach, like Scroll and Optimism Superchain and Polygon's Super Network. I don't remember the exact name, but we are trying to separating the layers. For example, for the layer 1, we are separating the data layer, consensus layer, execution layer. And actually, it is also same in the layer 2 also. So what I think is maybe almost of the layer 2 will be something like we commit the batch of transactions and then verify that in the optimistic way, which is having a game theory with the challenge logic, or verify the cryptographically. But actually, the reason why we are building the ZK EVM or trying to find a better or IVC is all are just to verify them cryptographically. But today, what I want to focus is the how to commit. Today, actually not talking about the how to verify cryptographically, but I'm going to talk about how to commit optimistically. So the current status quo is we are committing a batch of transactions, right? For layer 2, we collect transactions, the sequencers order them and submit the batch of transactions. But the problem here is, for example, I just personally think that the next of the account abstraction is the rollup chain, application rollup chain, which means if we have an account abstraction, there might be a sponsors, paymaster, and the paymaster actually getting some fee from you. For example, you are running an application. Actually, an application should pay some fee to the paymaster. For example, they will sell a kind of some NFT or game credit or something else, and they will let users use the network free, just like free. Actually, they are selling some products, and they're gonna pay some fee to the paymaster. So at some point, the application service providers will feel like, oh, I just feel like the fees are pretty expensive. So what is the most cheapest way? Is that actually they run their own sequencer for their rollup. But the problem here is maybe most of the applications will not have enough throughput to run their own sequencer. So for example, 0.1 TPS. And if it is pretty getting cheaper, if we should collect more than 100 transactions, then it just becomes like 1,000 seconds, which is more than 15 minutes. And it is very, very bad for the user experience, right? So what I am suggesting with the Schnorr signature here about commit a transaction instead of the batch of transactions. Let's see how we can just simply think sequencing a signature for every transaction, for every given transaction index. And the reason why we are using Schnorr signature is like it is pretty well fit for multi-party computation, the basic of the basic multi-party computation between and the sequencer. So they can complete a transaction signature together. And after that, they manage their signatures on their own data layer. So what we expect here is okay. So what we expect from this scheme is letting people do the state transition instantly. So let's think about the example. Simply, it is to say completing a signature between the user and sequencer together. So if they complete a signature, if the sequencer does not include that transaction into the given index, then the sequencer will get splashed. If that, we have a kind of a like 20 people here, and each of us are all the users, and I am the sequencer. And users can make a transaction and ask me an index to put this transaction into, and then we complete the signature together. So this is we have a transaction number 1 and its corresponding signature. And then we also make a signature together. And then we're gonna have a second transaction and its corresponding signature. So what do you expect here? If I have the series of the signature, then I'm gonna execute the state transition right away now, before we submit all of this data on chain. Because if the sequencer does not submit the exact data on chain, the sequencer will get slashed. And we can do it using the Schnorr signature. So it will allow us run a application-specific rollups, because it will allow us a low throughput system, but while it will also let us change the state instantly, which will be very, very good for the user experience. So this is the reason why this scheme was designed to. And for the next step, let's see what is Schnorr signature and how it works. First of all, this is just a basic of the Schnorr signature, and this is very, 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 it is the most easiest elliptic curve based signature scheme. So for example, you have a public key here, P, and what we want to do is, okay, I want to sign to a challenge value E using my private key. So here my private key is K. So, okay, then how about if I make a signature using S equals challenge times K, my private key. It's the most naive approach that we can make a signature, but you can just retrieve your private key K using the challenge value E and the signature value S, because we can just divide that, right? Yeah, let me just sit down. Because we can just divide it, divide the signature by the challenge value, then you're gonna retrieve the private key. So it is not safe. So to resolve this problem, what we do here is giving one more linear combination with a random nonce value R. If that, you just pick a random nonce R, which is kind of a salt, and then make a signature like S equals R plus EK, small r plus EK. Then to compute your private key using the signature and the challenge value, actually you also need to know the random nonce value itself. So it is pretty important to keep the private random nonce value here. And actually we are just providing its public random nonce large R to the signature verifier. This is how what is Schnorr signature? And is there anyone who can figure out the difference between this Schnorr signature and the ECDSA? These look pretty similar with each other. But the difference is actually it is not using the inverse of the private key. So it is very friendly for the homomorphism. So we can just do some linear combinations using a lot of Schnorr signatures together, which means it allows us combining multiple signatures in one group element. So, but actually there's also some problem. I think we can just skip this. The problem is the key cancellation attack, because it is easy to aggregate, because we can just say, you can compute your own signature and I compute my own signature, and we can just add these two signatures. But if we complete a signature using only this addition, then actually the other party can cancel your key just using its homomorphism. So how to prevent the key cancellation is actually using a weighted factor. So it is called mu-sig protocol. And before we combine two signatures, actually we are multiplying some weight factors to our public key. So this is all about how we compute the weight factor and finally aggregate them. And we can do it with a multiple parties, but in this example, I just brought an example when we just have two parties. So here is Alice and Bob, and they have their own private key, KA and KB. And public key will be like PA equals KAG, and Bob's will also same. And then after that, Alice picks her own random nonce value, small RA, and Bob also computes his own value, RB. And then now we start to compute the weight factor. The first is there might be some aggregated public nonce R, which is RA plus RB, and then compute some value using the hash function, and then compute Alice's own weight factor, and then Bob's own weight factor. Then actually, then if we just use the public key by Alice's public key plus Bob's public key, then it allows us some key cancellation attack. So to prevent it, we are having another aggregated public key, which is X, a weighted factor sum of public keys. So WAPA plus WBPB. And then compute a challenge value. The signature should be like a weight times the weight factor to your private key. Then we can finally complete a full Schnorr signature, which is safe from the key cancellation attack. Then using this mu-sig protocol, now I just want to introduce the detailed protocol about how the Schnorr sequencer works. So at first, so sequencer definitely should do some proof of stake, because if we submit a challenge, the sequencer should be able to be slashed. So at first we do some proof of stake, and then for the next step, is actually user build he or she his or her own transaction, and then compute the hash of the message. M is hash of the transaction, and then okay, pick a random nonce value of the user, small or u. We should be pretty careful here that we are not using the same random nonce value for the other stuffs. Yeah, just like ECDSA. And then compute the public nonce or large RU, which is a small RU times the generator. And also, we will gonna have a user's public key, PU. And we send this public nonce and user's public key and the hash of the transaction to the sequencer. The reason why we are only sending the hash of the transaction is because to mitigate the map as much as possible here. So we do not share the transaction here, and we share the transaction when we submit the partial signature. So at first, users provided those information to the sequencer, and then for the next step, sequencer computes the challenge and creates sequencer's partial signature, and then returns it to the user. Here, the challenge value E should be something like hash of the aggregate public key and the aggregate random nonce and hash of the message. This is a exactly same with the user Schnorr signature, but actually we add the index to include the transaction to the block here into the challenge value. So after computing this value, sequencer gives back the aggregate nonce value and aggregated public key value and the transaction index. Actually, not the signature yet. Then for the next step, okay. For the next step, user now also has the correct information to compute the challenge value. So now user finally can compute the partial signature using this E value and weight factor. I mean, to compute the weight factor, actually user needs the sequencer's public nonce value and also the challenge value. So user computes the weight factor and challenge value here and computes its partial signature. And then finally, submit this partial signature and the transaction to the sequencer. And for the next step, sequencer completes the signature and publish this data to the data layer. Then, yeah. Okay, I want to say about the map attack here. So what do you think that how we can do some map here? If you are the sequencer. If you are the sequencer, actually you can do some map attack like, okay, by this protocol, someone asked me about the index and I just returned that index like 7, but actually emptying the index for 6 to put some to put my own transaction before the transaction 7, right? Then what should we do? I mean, if you are the user, what you have to do to prevent it? You should create the signature if you're available to the previous signatures. If you are available all the signatures before the index number 6, then actually you are safe for the map attack. But actually, sense for a very, very high throughput system, but because we are targeting, I don't think that might be a big issue for the user experience here, because the period about the delay of the data propagation will not be a very big problem for the small network, for the application rollout itself. And if they are available for the older signatures, actually it might not be a problem. But to prevent it more technically, actually we can use the time lock cryptography here too. So the user user shares the partial signature and the transaction here, but not the transaction data. It's a encrypted data which can be resolved after a given amount of time using the VDF. So it is called time lock puzzle, and it will allow the sequencer just decrypt the encrypt data of the transaction after a given amount of time. We can add one more map resistance layer on top of it. But I don't think it's it might be a kind of some burden for the network to because the sequencer always have to compute all the time lock puzzle. So maybe user should share its decrypted cipher text before the sequencer decrypts it by time lock cryptography. But it means it is also one part of a attack approach. Yeah, so it will make some DOS attack by just letting the sequencer compute all the time lock puzzles. So what I think is maybe this approach might be much sense for applications such as games, which is not a sensitive to some map attacks like AMM or exchanges or DeFi related products. And this is about how to validate. Actually, we can validate using the pretty basic, only using the applications and additions, and we can do some challenge. But here, actually, one problem, the EVM is not supporting. Actually, what EVM now supporting for the EC Mar or EC add is only for the BN254 card. So, which means you need to build the Schnorr signature on top of the BN254 card. And actually, it's also a kind of a burden for the UX because you need to let users manage their own private key, which is in the maybe baby card field or the Scholar field of the BN254. So yeah, actually it's kind of a problem. So how we can resolve is maybe using account abstraction and also using zero knowledge proof to validate them, or maybe for the challenge system. So because this is all about the multiplications and addition, so very, very friendly inside of the ZK. So it might not take some cost inside of the ZK. So I think we can validate them massively inside of the ZKP. So when the user sequencer submits the batch of the transactions and signatures on chain, maybe the validity of the signatures might be proven inside of the ZKP pretty easily. So this is the approach that I'm thinking. And I talked about the math, and actually there are some other possible approaches. So the important thing here is about just we should commit with the transaction level, not the batch of the transactions, and sharing them through its own data layer will let us run our own application chain-based roll-up chain pretty easily. So because of it, all we have to do is just say committing a transaction and signing from both the user and the sequencer. Because of that, we can replace the Schnorr signature scheme with just a two ECDS signatures, just like Gnosis or PLS signature. There are some reasons that I think Schnorr is the currently best approach is that if we have a two ECDS signatures, the signature size will be like 130 bytes, 65 plus times 2. But Schnorr, it takes a 64 bytes. So it's a smaller than having a two ECDS signatures, which is pretty important for the rollup. But actually, it might be pretty different if we have the product and sharding, because the data price is getting more and more cheaper. And BLS aggregation is the problem with the BLS aggregation is pretty expensive on chain because we need to check the pairings. Actually, it is not that expensive in the computer. So we can just quickly verify and quickly prove the signature, but it is very expensive on chain. So maybe if we have a BLS pre-compilation, maybe it'll let us say, maybe we can replace the Schnorr signature with BLS at the time, or, but anyway, it is also not pretty friendly for the aggregation too. The aggregating, BLS signature is good for aggregating signatures against one challenge, but actually in our case, we have a multiple challenges. So one challenge for one transaction. So we need to aggregate all the BLS signature pairs. And it means like, if we aggregate 100 transactions, we need to implement the 100 pairing checks inside of the ZK Snark. So it might be a kind of a burden for when we aggregate them. So this is the reason why I think Schnorr is the best for now to implement this idea. But actually, definitely there might, EVM is always changing, and we are always having a better proving schemes and also better some cryptographic primitives. So I think one day we can change the Schnorr signature with others. Yeah, but yeah, I think for now, Schnorr is the best fit, has a best fit for this approach. Yeah, so conclusion is this approach is pretty suitable for the application rollups, and also maybe it is also suitable for account abstraction bundlers, because account abstraction bundlers also can have the map from transaction ordering, and it is a scheme that the sequencer committing the transaction orders by assigning every transaction index. So it is also can be used to account abstraction bundlers. And one limitation is actually its security depends on the amount of the proof of stake. So actually to increase the amount of these security, maybe BLS might be a better approach. But for example, if we have it is different with the consensus layer. We need to sign per transaction. So sometimes it doesn't make sense, like we have 10,000 validators, and if we make every 10,000 validators sign into one transaction, it will increase the security, but actually it will take a pretty long time. So very, very not good for the user experience. So I just think that maybe it is pretty suitable for a single sequencer model, but it is very important to take a note that single sequencer doesn't mean that it is not decentralized. You can decentralize the sequencers when you have a single sequencer model, just like it is called burn auction model. So it's making the sequencer to the right to be a sequencer in a permissionless way. So if you burn the sequencer for its next epoch or its next slot, so we can always implement the decentralized sequencer. Actually, it is something called a permissionless sequencer. And yeah, by the way, I think this is more suitable for a single sequencer model. So the limitation is the security depends on its proof of stake. So it is not suitable for some applications which has a huge amount of TVL. So I think this is not good for the model. This is much suitable for maybe something like games or much easier some applications. Yep. And also we can use a content abstraction and ZK for the scaling. Yeah, this is about the Schnorr sequencer. Transaction. And sync and publish that. What I want to recommend is all the construct a peer-to-peer network and sharing the signatures through their peer-to-peer network. So for example, and we should be a P2P node. And whenever the signs a transaction, this will be published or others. This is the most optimal approach. Also, if you just trust the sequencer, actually you can just fetch the signature data from sequencer's API. But I just think peer-to-peer might be a better approach. Valid transaction. Yeah. Actually, so the validation is another part. So this is only about the commit part. Yeah. So you should implement the validation logic later. Yeah. I propagate it to. Yep. So when the user wants to submit a transaction, user submits the basic data, and then actually the sequencer gives back the index to complete the signature together. So sequencers always should manage the queue. The total number of the published transaction, it should be just shared by the peer-to-peer network. So it is something like there might be 3 parties: sequencer, Alice, Bob, and at first Alice will have a transaction data of 5 and sequencer 5, and Bob will have only 4. But they should propagate all the transaction and signature data through the peer-to-peer network, just like Ethereum layer 1 does. And Bob should not execute the transaction, the index number 5, before Bob is available for the transaction data and also its signature, Schnorr signature data. Yeah.
What if I just two users ask the index?
It should be managed by the sequencer using the queue, so using the software. Yeah, user should have a queue, and yeah. I mean, sequencer should manage the queue. Okay. Yep.
Yeah. So if I understand correctly, this design allow user and sequencer to commit to the transaction at a certain point.
Right.
And then the rest come from proof of stake style /
right.
Which in turn would also mean that actually you can design any type of sequencing mechanism so that you can have function of certain index, you can allow people to basically anything as long as proof of stake mechanism.
Yeah, so it is all, yeah. So can you repeat your question exactly? I mean,
so the question is actually that this process allow you to, the protocol itself just allow you to commit to an index.
Right.
And the rest kind of thing that you can change around, whether if you're gonna do first in first out, which is verify whether they already commit to the previous index, but there's nothing stop you from doing this without doing that process. So it's a different behavior that you can auto customize this Schnorr style index from that.
Actually, I didn't understand the correct question.
Okay. So the question is actually if this decided that you can commit to commit a transaction to an index and both parties side, you can kind of have different mechanisms to decide which transaction
right.
Where. So,
yeah, right. So yeah, that's the reason why we have multiple approaches to achieve this goal. Schnorr is just one of them, and we can also basically we can use PLS definitely. Yeah.
Do you think this scheme is to implement AAS in the center?
I think so. Yeah, I just think having an account abstraction along with this sequencer might be better. Yeah.
Is it what they're doing now?
Who are using?
Is the war on the alternatives?
Which one was the majority?
She was considered as the majority right now.
I just released this only a few weeks ago, so I'm just saying, yeah, yeah, to say initiating the initiatives. Yeah, yeah. And yeah. Mhm.
Collaboration.
This is not a collaboration, and it is we are very open to the collaboration anytime. So if anyone wants to implement this Schnorr sequencer based I just think like we need to tweak the current execution layer because I just recommend constructing a peer-to-peer network to use this approach. And then, yeah, if someone wants to do that, actually, I think we are pretty ready to support them. Yeah, actually, some people reached out to me, but yeah, because there was a Tokyo Taipei, I'm traveling like from February, so yeah, maybe after having a few days of some day off, I'm gonna talk to them again. Yeah, so there are some people who want to implement this, and I think that we can have a various version of clients using this sequencer model because it can be combined with the abstraction, or it can be combined with the zero knowledge proof for the validation, or also for the challenge system, etc. So there might be various versions. So I think I don't think that we might support only one party. Okay, great. Then shall we go to the next topic, the KZG RLN? It's a kind of a not